Welcome on board. This is Design B Engineering Process, a channel where we give a walkthrough on process engineering operations and design. Let's dive in. Oh, engineers in the rough, we have a design mission on hand. Your mission, should you choose to accept it, simulate the production of hydrogen gas and oxygen gas via water electrolysis using an alkaline electrolysis system. Conditions include our feed composition. We're going to be having water, 100% water, for a single stream, and another stream of potassium hydroxide, 100%. Feed conditions for our water include 1 bar or equivalent to 1 atmospheric pressure, 1 atm, and a flow rate of 5,000 kilogram per hour. That's mass flow rate. The process setup for the electrolyzer configuration, we have the electrolyzer inlet stream conditions to be at a temperature of 70 Celsius or greater and a pressure of 7 bar. That's the stream going inside the electrolyzer, the inlet. Inside the electrolyzer, number of cells we have 200. Number of stacks we're working with 1. Already efficiency 93%. Pressure drop inside our electrolyzer 0.5 bar. Split ratio 0.5, and the electrolysis reaction as follows. Now, the electrolyzer configuration is just for the purpose of this. For the purpose of this content, it's basically made up. We're just going to use it to work for the purpose of this design mission. And for product yield targets, we're having hydrogen gas. We're expected to have a yield of greater than 95% hydrogen in mole fraction. And for the oxygen, also a yield of greater than 95% oxygen. So with this, we have the preliminary information we need to start our modeling, even though some minor important information is missing. Things like our food package, our food package, and also the conditions of our potassium hydroxide stream. We only know that it's 100%. We're going to create a stream of 100% potassium hydroxide, but we do not know the feed conditions for the potassium hydroxide. So as always, it's design simulation. We have to carry out some research. So let's head to the Aspen Hysys environment. Currently on the Aspen Hysys environment, we are not on the simulation environment on the get-go. And the reason for that is that we're going to be having a bit of a detour. We're going to derail a bit from the usual route we take for our simulation. Firstly, if you currently know how to create the component list and fluid package, you're at the right dimension. You're currently in the right dimension at the right time. So previously, other than now, or looking back at how we have been creating our component list and fluid package, we have been using the Hysys option and not the Aspen properties. Today we're going to be using the Aspen properties. And this is what it looks like. It looks slightly different from our Hysys interface when using the Hysys interface to create component list of package. And how we find our component lists here is we click on search and type whatever we're looking for. And for our components, we're going to be working with water, okay, potassium hydroxide, potassium hydroxide, good, hydrogen gas, oxygen gas, good. With this, we have successfully created our component list. And looking back at our reaction for electrolysis, these are all the components interacting in the reaction. Even though we do have an extra potassium hydroxide, but we're going to explain why it's there. It doesn't take place in the reaction, the electrolysis reaction. Now, what exactly is water electrolysis all about? It's a process used to generate water and to generate hydrogen gas and oxygen gas from water using electricity and some other phenomena. It's a good way of producing water. It's a good way of producing hydrogen gas and oxygen gas. In our previous content, we discussed using cryogenic distillation to separate the mixture of air into distinct components of hydrogen and oxygen. Today we are using water electrolysis to separate that mixture into hydrogen gas and oxygen gas also. Now, to do that, we require a fluid package as always, and our fluid package is going to be under Aspen properties also. As you can see, for the fluid package, we have a third option, which is thermal, but we are doing away with that for now. We're going to work with the Aspen properties, and the fluid package of the day is electrolyte NRTL, not the very versatile Mr. Penn Robinson. Electrolyte wizard. Now, this is the reason why we are working with Aspen properties today. The only function in Aspen Hysys, the only place we can see electrolyte wizard is when we work with Aspen properties. If we're working with Hysys, we do not have that function available. For Aspen Hysys, we need to work with the Aspen properties to be able to access electrolyte wizard function. And the electrolyte wizard function is where we specify our electrolysis, the stage where we specify the inbuilt reaction for the electrolysis and also water dissociation. Basically, water dissociation. That's what it's all about. Reason why we're working with the water dissociation, where the breakdown occurs for the ions involved in this reaction. And as you can see, we have all the compounds, the components that we selected, and you could just get reactions. And with this, we have reactions. Now up here is the reaction that we have for the water dissociation, and down here you could also see another reaction involving potassium hydroxide. And the reason why we're using potassium hydroxide for this process is that in water electrolysis, we require electricity to carry out water dissociation, generate hydrogen gas and oxygen gas, basically breaking that bond between them in water. And to do that, water needs to conduct electricity, and water in its natural form is a poor conductor of electricity. And as such, we introduce a salt, which is potassium hydroxide, to improve the conductivity of water. With this, it makes it a better conductor of electricity, and it improves our efficiency performance for producing hydrogen gas and oxygen gas in the process. So that's the reason why we're having potassium hydroxide in this process. So with this, we have generated our reactions. Remember, we're working with water dissociation, not salt formation or ice formation, and the hydrogen ion type is H plus, not H3O plus. So with this, we could just make sure we're selecting all the equations, select all, and then click OK. And we could head to the simulation environment. It's going to take a bit of time because of the electrolyte wizard to get things in place. So we're currently on the simulation and modeling environment, and as always, we create our stream. But remember, we're having two streams. It's just potassium hydroxide stream and water stream. Now, for the potassium hydroxide stream, we were not given conditions. We were only given that we have a stream of 100% potassium hydroxide, but we do not know the conditions of the potassium hydroxide. So based on research, we were able to understand that we need to use a fluid package of electrolyte NRTL, and also for the potassium hydroxide, we need our conditions to be something similar to the conditions of water with respect to temperature, which is atmospheric pressure and room temperature, which is 25 Celsius. We're working with 25 Celsius and 1 atm, which is also 1 bar, equivalent to 1 bar. And for the molar flow rates, usually it has a ratio. When working with the potassium hydroxide, you need about 20 to 30% of the feed of water. That's what you need for a potassium hydroxide. So we're going to be adding about 20 to 30% of our water worth of water as our potassium hydroxide. Remember, the flow rates for our water is 5,000 kilogram per hour in mass flow. So working with between 20 to 30% for our between 20 to 30% for our potassium hydroxide, we could work with something like 1,500. That's decent for our mass flow. 1,500 kilogram per hour, and you just need to specify this 100% potassium hydroxide, which is 1 Alright, we have successfully created our stream. It's completely liquid, 25 Celsius, 1 bar equivalent to 1 ATM, 1500 kilogram per hour, and a molar flow rate of 26.74 kilogram mole per hour. That's for potassium hydroxide. Let's just fix this up. POH, potassium hydroxide, and the stream is our H2O, water, and the temperature from our design conditions 25 Celsius, 1 bar equivalent to 1 ATM, and the mass flow rate of 5,000 kilograms per hour, 100% water. Yes, and we have successfully created our stream. All right, so to add potassium hydroxide to our water, we just need to mix. H2O, and we could call this, let's just say mixed. Let's just call it mixed. All right, bit more space, and let's look at the condition after mixing. All right, as you can see, our vapor fraction, we gained gases, about 70% gas and 80%, approximately 80% made up of 80% gas and 20% liquid. And what we have here for hydrogen or water, it's completely liquid. The potassium hydroxide is completely liquid. The temperature, 25 Celsius. For water, also 25 Celsius. We have an increment. For water, we have an increment. Our temperature raised. So our temperature was raised from 25 Celsius to 156.2 Celsius. And the reason for this is that the reaction between water and potassium hydroxide is exothermic, if I'm right. Pardon me if I'm wrong. I'm not a chemistry guru, but I believe it's exothermic. It generates a lot of heat. From elementary chemistry, practically, when you place potassium hydroxide inside water, you notice heat's being generated, and most times you could see bubbles. It's fizzy. You see heat vapors being formed. So it's similar to that chemically. Talking about the chemical reaction, that's why we have increment in our heat from 25 Celsius to 156.2 Celsius. Now, remember from our design conditions, to go inside our electrolyzer, the inlet condition must be 70 Celsius or greater than 70 Celsius and at a pressure of 7 bar. So we need to, in our scenario right now, in our case right now, we have more than the required temperature. So I wouldn't really say more than the required temperature because it says greater than 70 Celsius. But at the same time, I think it's a bit too much for the electrolyzer. We could just drop it around 70 or 80, between 70 or 80. So we could just work with 80, I think. And to do that, we need to drop our temperature, and equipment that drop our temperature include coolers, the exchangers, refrigeration cycle. We could just work with a cooler to keep things simple for the design. But I'm not really here to use a heat exchanger because it's energy efficient. So plug this in, call this e-cooler, this cool, we just call this cool, specify change in pressure. Let's say we lose 0.5 bar, 0.5 bar, and the temperature is cooled down to 80 Celsius. 80, that's decent. Decent, we could say 80, decent. So We've dropped our pressure to the desired, our temperature rather, to the desired condition, and we have to work on the pressure also to increase the pressure. Okay, it's completely liquid, so we could just pump liquid in white as well. You wouldn't really want to do it that way. I think a good approach would be pump. Let's see. Liquid. I think a good action would be to pump them to the mixer. And that would be better. And then Aspen Hysys, it doesn't really matter, but just to make things look cool. Make this, add a pump for water. Let's see, design H2O, pumped H2O, heat pump. Cool. So, change in pressure from 1 bar to 7 bar, that means we need an increment of 6 bar, but let's account for pressure drop inside our cooler, which is about 0.5 bar, so we could just make this 6.5 bar. Cool. We have 7.5 bar. I think we good to go. Another interesting function that I found out just recently on Aspen Hysys was that you could you could move this label because it's always annoying covering the lines. You could move it. Who else knew you could do that? Just finding out recently. So also drop a pump. You drop a pump for potassium hydroxide. We're going to be pumping that also. Potassium hydroxide pumped. POH, potassium hydroxide, and E pump 2. For the parameters, the same thing. 6.5 change in pressure gives us 7.5, which it does. Right. You've got to be kidding me. It's completely gas after pumping to that pressure. Oh, but our water is still liquid. Potassium hydroxide turned to gas. No matter. Just mix them up like that. H2, pump potassium hydroxide. Good. Let's see what our mix looks like. Right, the same vapor fraction as before, but the temperature currently is 217.2. It became even worse because of the increment in pressure. Increment in pressure and also the reaction between the potassium hydroxide and water, exothermic. So we need to be 7 here. We lost 5 bar. It's pressure loss and at temperature of 80 Celsius. I think that works. So time to work with our electrolyzer. The electrolyzer is the third to the last, that's a word, to the last equipment on our model palette. Electrolyzer, and this is what it looks like. Right. So we're thinking, and this is what it's quite large. Just minimize this. Very large. Right, much better. This is what the electrolyzer looks like. And we have two sides for the electrolyzer. Starting with that, we have the anode outlet and the cathode outlet. And from our elementary chemistry, we also know what that means. And if we don't, it's the anode is the positive side of the electrode the positive side electrode, and for the cathode, it's the negative side electrode. So in a chemical reaction, the positive ions go to the negative side because, like from physics, like charges repel and dislike charges attract themselves. So positive and negative attract themselves. So the positive ions go to the cathode and the negative ions go to the anode. So with that, we have to specify an anode outlet and the cathode outlet from our electrolysis reaction. The positive ions is the hydrogen and the negative is the oxygen because it's H plus and O negative. That's how it is. So for the anode, we're going to specify, we expect the oxygen gas to be here. So it's O negative. No, O negative. Why are we having hydrogen coming here? Let's specify the inlet first of all. Cool. Not hydrogen. We have an hydrogen H2O, 30 plus O2. Thank you. And here we have the positive H plus. H plus. This is O negative, not O2. O negative. Much better. And you can see we have a message down here, requires power stream. So this is where the third stream in our update comes into play. Power stream. Ordinarily in our previous contents, we just have two, in our previous versions for Aspen Hysys, rather around version 12 and below, we just have two streams, the energy and material stream. But the update version 14 comes with a power stream, and this is where we use our power stream. It comes in handy. It's the yellow one. We just delete this. I forgot to mention that if you are using an Aspen Hysys version that is less than anything around version 12 and below, I don't think there's an electrolyzer in the model palette, and as such, you have to use a reactor to carry out water electrolysis. Sorry to bust your bubble. I should have mentioned that earlier in the content. But if you're here, extra knowledge, no knowledge is a waste. So you require a power stream in our electrolyzer, and we have computed the power stream, but we also have to specify. And the energy stream, it's optional. And before we move on, we have some configurations for the electrolyzer, which we should also look at. Single feed stack, it just basically means that we have one single inlet. If you're using double feed, we have double. We're using the single feed. For the electrolyzer model, it's a bit complex. We do not need that for now. Then rigorous, when you want to handle more complex electrolyzer processes, we're keeping it simple. We're just going to work with the simple single feed stack configuration for the electrolyzer. Now for the parameters, this is where we specify our power, and we also were not given an information on power regarding the power we need for our electrolyzer, so we have to do a bit of research or trial and error. We were given the number of stacks, however, and the number of cells, 200. The number of stacks is just 200 cells per stack. Power consumption consumed per stack, dependent on the power we specify. So we're going to start with about 10 kilowatts to see how it goes. It's quite on the low side, but we just want to see how it goes using 10 kilowatts. Now we need to specify, okay, the pressure drop also 0.5 bar. Now we need to specify either our duty or outlet temperature for the electrolyzer to solve. And I think it's going to be better if we specify the outlet temperature that we require. It's just like our heat exchangers and coolers where we have to specify the temperature for it to solve sometimes. So the outlet temperature, let's say we lose about 5 Celsius in the process. 5 Celsius. On the high side, let's just say 5 Celsius, 75 Celsius, and boom. Remember, we specified a pressure drop of 0.5 bar, and that's why we're having 6.5 as the outlet. And we lost 75, so we lost 5 Celsius, and that's why we're having 75 here. And as you can see, we have successfully solved our electrolyzer using 10 kilowatts, and our duty is here about 25,000. And as you can see, the power consumed per stack, because we only have one stack, the whole power goes to that stack. 10,000 kilowatts. Faraday efficiency, we will also have to specify this is 93% from our information given. And what we have here is the higher heating value efficiency, lower heating value efficiency, voltage efficiency, and you could switch in between them, whichever one you wish to specify. In case we're just going to work with the inbuilt, the higher heating value. Let's just leave it on that. 93% gives us 100% higher heating value. So right now we need to look at our composition, see the hydrogen yields, what it looks like, basically the hydrogen percentage, and this is what it looks like. This is our inlet stream to the electrolyzer. These are our outlets, and inside our outlets for oxygen, we barely generated any oxygen. It's so insignificant. For the hydrogen, it's the same thing. As you can see, we still have 91% water present, and also 91% water present, and mostly the potassium hydroxide also 8%, approximately 9%, 9%. So we basically did not generate any oxygen or hydrogen. So with this, we understand that we have to tweak our operation conditions, and it's majorly dependent on your power. The amount of hydrogen gas you produce is majorly dependent. Hydrogen and oxygen gas and electrolysis is majorly dependent on your electricity. So electricity power basically. So we have to increase our power inputs.